Rahul sir?
I'm audible, sir?
Yes, sir.
Okay, okay, I shall begin with the session on molecular dynamics simulation.
Just a minute, sir.
Let me share the slide. Can you able to see the slide, sir? Is it visible to everyone?
Yes, sir.
Okay. I'm once again, good morning to everyone. Once again, I'm thankful to Shah sir for giving me the opportunity to conduct a session, one more session on molecular dynamics simulation. Okay. So basically, molecular dynamics simulation is extensively used in the computational chemistry. In drug discovery, what we do, we identify the new compound as a hit molecule, then we establish the stability of that compound. And to establish the stability of that drug receptor complex, we used molecular dynamic simulation. During molecular dynamic simulation, we ascertain different parameters to check the stability of the drug receptor complex. For example, we check the root mean square deviation of the protein molecule. Okay, so if we conducting a simulation for some 50 nanosecond or 100 nanosecond time period. Okay, so during that we observe the fluctuation of the protein which is bound to the ligand molecule throughout the 100 nanosecond. If that particular protein molecule RMSD fall below 3 angstrom, then it is clear, it is decided as a stability of the drug receptor complex. Okay, so let us begin with the molecular dynamic simulation. Okay, so basically it is a computational simulation technique used to study how atom and molecules move over the time. So what happened when we begin the molecular dynamic simulation?
Hello. Rahul sir?
Sir.
Just a minute, sir. I think there is a problem with recording. I'll again.
Okay, sure, sir.
A minute, just a minute.
Okay.
Yes, sir. You can start now.
See, molecular dynamic simulation is one of the key techniques in drug discovery. This technique is used to establish the stability of the novel chemical entity, which is identified by molecular dynamic simulation. During molecular dynamic simulation, we observe the stability of the protein to which the ligand molecule is bound. And we ascertain the stability, we cross-check the stability by verifying different parameters. We go for RMSD, and we go for type of hydrogen bonding contact, because the hydrogen bonding contact which is made by the ligand during molecular docking must be sustained in the end of the simulation, or it can make some more contact also, but still because the activity of that ligand or the stability of the ligand depend on the key bonding contact with the receptor molecule. Then we also check some more parameters like radius of gyration. Then we check the hydrogen bonding contact, then we check the hydrophobic contact, then we check the solvent accessible surface area and some more contact. Moreover, apart from RMSD, we hydrogen bonding contact or interaction contact, we check the root mean square fluctuation of the protein molecule. Okay, see, the nascent protein or the protein without ligand is highly flexible. Okay, and when any ligand bound to that protein, its fluctuation become reduced. Okay, and that same thing we observed in the root mean square fluctuation graph. Then we cross check the uh, hydrogen, the 2D interaction by using some bar plot. Then we check the some other parameters like we evaluate the ligand molecule also for different parameters like solvent accessible surface area, then radius of gyration, okay, and some more. So let us begin with this molecular dynamic simulation. Basically, this is a computer simulation method that is used how atoms and molecule move over time. See, we cannot predict the environment of the binding pocket of the receptor where the ligand is situated. Okay, so to explore that movement of atom within the movement of atom of the ligand molecule and the protein molecule over a particular period of time, we use this technique, basically molecular dynamics. So what it does actually, it helps scientists, researcher to understand how drug interact with biological molecule such as protein or DNA at the atomic level. Okay, see, it not only explore the interaction of the drug molecule with the biological molecule or macromolecule for a period of time, but we come to know what exactly happened when the molecule stay in the binding pocket for a particular duration of time, for example 100 nanoseconds. Then this basically this simulation combine physics, chemistry, and computing to model real molecular behavior that happens in nanosecond to microsecond time scale, too fast to observe directly in experimental. So, if you wish to observe the atomic level interaction of one ligand which is situated in the binding pocket of the receptor by any empirical method, uh, that is not at all possible. So this method combine some biophysics with the chemistry along with the computer to observe the behavior, the movement of the molecule, how long it sustained the established hydrogen bonding contact during molecular docking till the end of particular simulation time period. Okay. See, the fundamental idea of the molecule dynamic simulation is based on Newton's second law of motion. So this Newton's second law of motion explore on how atoms in a molecule interact and where they start, and how we can calculate their movement over the particular period of time. Okay, so in MD, forces are calculated from potential energy function, and the position of atom are updated step by step over time. The Newton second law of motion is F is equals to m into a. F stand for the force on each atom, then m stand for the mass of atom, and a for the acceleration, that is change in the velocity. See, all these three parameter, force, mass, and the acceleration, are associated with the single atom which underwent for the moment during the molecular dynamic simulation. Because see what happened when we initiate or begin with the molecular simulation, we apply certain forces. Okay, we vibrate entire system. Okay, so the atom which is present in the system underwent for certain acceleration with certain mass. Okay, that's why it is based on the Newton's second law of motion. Then potential energy and force field. Atoms in molecule interact through bond and unbonded forces, and a force field which is used to calculate the movement of that atom is a kind of mathematical model that describes the interaction. See, when the atom moved in the system due to vibration applied during the molecular dynamics simulation, they interact with each other. Okay, during molecular dynamics simulation, what we does, we try to mimic the physiological condition at a particular pH. So we supply certain ions, we supply certain water molecule, and somewhere the functional group which is present in the ligand molecule interact with those ion, interact with those water molecule which is added during the system preparation, and finally this force field calculate this moment in the form of some RMSD value or some RMSA value. Okay, so basically the total energy of the system is calculated as the summation of energy of the bond, which is formed and detached during the molecular dynamic simulation, because the atom of the system, atom in the system of the drug receptor complex are continuously making and breaking the bond. Therefore, this force field calculate this energy bond. Then they also calculate the energy of the angles, then energy of the diagonal angle, then the electrostatic interaction, which happens during the molecular dynamic simulation, and some van der Waals contact or some hydrophobic contact, which happens during the run of molecular dynamic simulation. So some force field which is used to capture these changes happens to the atom during the molecular dynamic simulation are amber, which is used for biomolecules like protein, DNA, RNA. See, if you are going for the MD simulation of simple any macromolecule or biomolecule, then you have to select the force field called amber. Simultaneously, if you are going for the MD simulation of DNA and the RNA, then you have to select this charm amber force field. Then when we go for the analysis of dynamics of protein and the ligand system, in that case we have to select the charm, and obviously the GROMAC for both organic and biomolecular system, especially in pharmaceutics. In pharmaceutics, we analyze the complex of drug and the certain metals. Okay, in that case, the GROMACs will be very useful to explore the behavior of or stability of the metal ligand complex or metal drug complex, metal biomolecule complex. For example, when we simulate a COVID-19 main protease inhibitor complex, a force field like Umber FF40SB is used to calculate forces between atoms. Okay. See, in GROMACs, different force fields are available, but in Desmond, only one force field is there, that is OPLS 2003 and OPLS 2005. So while protein preparation, we have to select the force field OPLS 2005, which is latest one in the Desmond software. Subsequently, there is integration of equation of motion in GROMAC software. This include one forces are known. MD calculate how atom move using numerical integration algorithms such as variate algorithm, leapfrog algorithm, velocity overload algorithm. See, all these algorithms are exclusively used in the GROMAC software, and these are used to calculate the moment of the atom, and they calculate the result in the form of different simulation parameters. See, this method update atomic positions and velocity every 1 to 2 femtoseconds. 1 femtosequence is equals to 10 to the power minus 50 second. For example, for a 100 nanosecond simulation, around 50 million steps are calculated to capture the detailed motion of all atoms. So in the MD simulation, we not only capture the moment of ligand molecule, but also we capture all the moment of all the atom which is contained in a particular protein molecule. For example, a protein molecule having a size of some 2000 or 5000 atom. So for the time period of 100 nanosecond, MD simulation study capture the moment of all the 3000 5000 atom which is contained in that particular protein molecule. Then the thermodynamic ensemble, which include MD simulation condition, in which we always we implement the MD simulation with particular condition, and that conditions are called as ensembles. Okay. For example, in protein drug simulation, the NPT ensemble is used to mimic the body's temperature 310 K and pressure 1 atom. See, while selection of the MD simulation, while running the MD simulation, we will have one dialog box. In that, ensembles are mentioned. Okay, if we are using any drug, any biological system, biological conditions like drug receptor complex. In that case, we have to go for the NPT. If we want to check, or if we want to ascertain the thermal stability of the drug receptor complex, then we have to go for NVT. And if we are going to study the energy conservation of the drug receptor complex, in that case, drug receptor complex or any other complex or metal organic complex or the macromolecule metal organic complex, in that case we have to go for the NVE, that is number, volume and energy ensembles. Is there any question on the session covered till now? Dear participants, is there any question on the molecular dynamics simulation part which is covered in your last slides?
Sir, one question
No,
is
sir.
there.
Okay.
How to select specific force field for specific protein complex? One question is there in chat box.
Yeah, see, in Desmond, we don't have any option. Okay, we have only force field 2003 and force field 2005. Okay, so Desmond offered only one force field, so we have to select that one. But in GROMAC, some other force fields are available like Amber, then CHAM and GROMAC. So whenever we have the analysis of any biomolecule without any ligand, like protein, DNA, or RNA, in that case, we go for the Amber. Then when we go for the analysis of protein ligand system, then in that case, CHAM is the base force field to analyze the movement of atom within the protein ligand complex. Then in GROMAX, they itself have their software GROMOS for analysis of both organic and biomolecular system. For protein ligand also, we can use this GROMOS force field. Is it clear for now? Is it clear, sir?
Yes, sir. Few more questions are there.
Okay.
In GROMAC, we may get many force field, and is 100 nanosecond compulsory? Any justification if performed for less time?
See, there is no such time period for performing the MD simulation. It depends on your study, okay, and it depends on the stability of your protein, okay. If you started a MD simulation for 100 nanosecond and you are not getting the correct parameter at the end of the simulation, in that case, you have to extend your simulation to 200 or 300, okay. Moreover, chat box. Okay. I think it is clear with you. Okay.
Yes,
Sir, in certain cases, what we does, we go for the triplicate MD simulation if we get appropriate result in the first run of the simulation. Okay. In most of the journal, they suggest to go for triplicate MD simulation, and finally, while presenting the result, we draw the overlay spectra or overlay spectra of the RMSD, RMSF, and some other parameters like hydrogen bonding and some radius of gyration parameters. Okay.
Okay, sir. I have one or two more questions.
Okay.
While submitting article in journal, so various reviewers asking about docking validations. So
Okay.
docking validation, that is okay, but sometimes they are also asked for MD validation. So it is same answer as you just mentions. Okay, we have to perform MD for 3 times.
Yeah, this is very good question. Sir, actually, the docking validation is of 2 types. Okay. First validation we perform by redocking the co-crystallized ligand. Okay. And second validation we perform with the MD simulation. So in both fashion we have to justify the answer of the reviewer.
Okay. And one more question, sir.
Okay.
Sometimes what happen? Okay, we get good result with 100 nanoseconds, but
Okay.
journal is asking for perform MD simulation for 300 or 500 nanoseconds. So how to answer this query?
See, if we observed high fluctuation uh, in the moment of the protein in the RMSD plot, in that case, they recommend you to, or they suggest you to go for high end or high time period MD simulation. Okay. And if the protein ligand complex is highly stable below 2 angstrom or below 3 angstrom, like, then they won't suggest you to go for the simulation for a longer duration of time. See, in that case, what we can do, we can perform triplicate MD simulation. Okay, and with the help of Excel, we can overlay the RMSD plot, hydrogen bonding plot, and the RMSF plot, and likewise, we can justify the answer of the.
Okay, sir. Thank you.
So the next we have a periodic boundary condition. See, after preparation of the system for molecular docking, we have to prepare one grid box. Okay, and that grid box is called as periodic boundary condition. Okay, so what it does, it mimic an infinite system and avoid surface effect. The system is placed in a box of repeating images. Repeating images means we filled that entire grid box, or we called as we referred it as a system building in MD simulation, with a lot of water molecule, lot of physiological buffers at particular pH. Okay, so when an atom leaves one side of the box, it re-entered from the opposite side. So that's why they are just like a repeated images. Okay, if you observe the build system built in the MD simulation, it is just like a partition. Okay, and the example is a protein ligand complex is placed in a water box, and PVC ensure that the solvent behave naturally as in the real biological system or biological environment. See, one of the key aspect to build the periodic boundary condition or grid box is to mimic the real physiological condition or real biological environment. What happened? During MD simulation, we mimic the total condition of the binding site of the receptor, where all buffers, particular pH, the ligand, and everything is present along with the water molecule. And we vibrate the system with all this solvent and buffers at particular pH, and see and observe the movement of the molecule within the receptor binding pocket, whether it sustained a bond with the particular um, uh, functional group of the residue, amino acid residue of the receptor or not, or whether it if it detach himself from the all the bonding contact, then the end of the simulation will be failed. Okay, such simulation is not successful, and we will get the RMSD above 3 angstrom, or it will extend to 9 or 10 angstrom also. Then the basic workflow of the molecular dynamic simulation is the system preparation. So this include building a protein ligand complex. So one protein preparation wizard is there in the Maestro Desmond module. Using that, we can prepare the system, which is a kind of protein ligand, which is nothing but the protein ligand complex obtained from the molecular docking. Then further we go for the energy minimization. We remove bad contact. This also we perform during the molecular dynamic simulation. In certain cases, during the protein preparation, we remove some unnecessary chains from the protein molecule. Okay, see, the simulation of the time required to complete the simulation depend on the number of atoms present in the system. Okay, if we if we cut some chains from the protein ligand complex from the protein molecule, then our simulation time get reduced. Okay, then equilibrium is also a part of system preparation. Then it stabilize the temperature of the pressure using NVT and NPT. Then production run, we go in this, we go for the 100 nanosecond simulation or 50 or 20 nanosecond simulation, and during the trajectory analysis, we evaluate the system behavior, that is for the RMSD, RMSF, and binding energy like parameters. Okay, these the key quantitative analysis which we achieved or which we observed and explored during the molecular dynamics simulation are root mean square deviation that measure the system stability, and it is used to check if ligand remains stable in the binding site. Okay, so there are certain criteria put forth to check the stability of the drug within the binding site of the ligand molecule or the complex. If the RMSD observed below 3 angstrom, then we can say that in that case the system is highly stable. If RMSD is trending beyond 5 or beyond 6 or more than 3, then that system is not stable, and in such case reviewer recommend you to reperform the MD simulation. Then second parameter which is very useful to assess the quality of the MD simulation result is RMSF, which measures the flexibility of the residue, and it identifies flexible binding region. See, if we analyze the single protein for MD, then we observe a lot of fluctuation in the protein molecule. And after that, if we go for the analysis of drug receptor complex for RMSF parameter, in that case we found less fluctuation as compared to the single protein, or native protein both. Okay? Then we go for the analysis of radius of gyration, which indicate compactness of the protein. Okay, so this parameter is used to cross check the geometric fit of the ligand within the receptor binding pocket. Okay, lesser the value of the radius of gyration in the simulation study, higher will be the stability of that drug receptor complex. So it studies protein folding stability. Then hydrogen bonding track key molecular interaction and ensure stable. It is used to ensure stable ligand binding. We always cross check whether the contact which is formed by the ligand during the molecular docking is sustained at the end of simulation or not. Okay, then we estimate the binding free energy which is released during the completion of the simulation by using the MMGPSA. Lekin this module is not available in the Desmond software, so we have to go for the Schrodinger. Okay, it is available in the Schrodinger. There are two methods to evaluate MMGPSA or MMPPSA in the Schrodinger software. One, in one way, if you after finishing the docking and say same docking complex, you can analyze for the MMGPSA and MMPPSA, or we have a second option to perform MMGPSA PPSA. We can analyze the simulation complex for the GPSA with certain command in the Desmond software. Okay, then obviously it is used extensively in the drug discovery. That's why it finds its different place in the computational chemistry as well as drug discovery. So it serves as powerful complement to experiment. So we can use MD simulation as an alternative to the experimental technique. Okay, see, simple visualization of the drug receptor complex cannot give you the idea about the stability of that complex. Okay, so by performing simple docking followed by the MD simulation, we can check the stability of the drug receptor complex before going for any empirical study. Okay, so this is used in the different stages of drug discovery, like hit identification. In this case, it tests binding stability of the virtual heat, and it is extensively used, successfully used in the COVID-19 protease inhibitor discovery. Then further, it is used in the lead optimization. It is used to refine binding interaction, and using this lead and BRF kinase inhibitors were successfully identified by lead optimization feature in molecular dynamic simulation. Then we can reveal the mechanism of any ligand molecule, how it behave in the receptor binding pocket. We can capture the conformational changes, what type of conformation it is acquired during the entire simulation time period. Okay, what is the conformation at the beginning of the solution of the simulation, and what is the conformation at the end of the simulation. So this mechanism was established for the GPCR activation study. Then it is used to predict the resistance, test effect of mutation. Okay. Yesterday I have discussed one example of ABL kinase. Okay, in during the case study in molecular docking. Okay, so the people of Novartis come up with the idea of mutation in the threonine residue. Okay, which is replaced with another residue. So they perform the MD simulation and they cross-check the behavior or fluctuation of the behavior of the protein molecule, and with that they establish the particular mutation occurrence or observation of particular mutation in the protein molecule. Then in formulation design also it is used. The MD plays crucial role in drug stability study in carrier, and it is specifically used in the liposomal formulation. So this is one of the publication we had in the scientific reports, and for this I am very much thankful to Umang Shah sir. He helped us in completing the in vitro MTT assay on triple negative breast cancer and skin cancer. So the objective of this in this manuscript is to assess stability, binding dynamic, and the conformational behavior of two potential EPR inhibitors, C878-1660 and D685-0061 through 500 nanosecond molecular dynamic simulation. Okay. See, in this study, we have performed QSAR modeling. That is followed by the QSAR based virtual screening. In that, we have predicted the biological activity of some specific database downloaded from the KMDIB database, and we have obtained certain hit molecule with a good predicted activity by QSAR. Simultaneously, we have performed molecular dynamic simulation on the dataset molecule, and the molecule which we have obtained as a hit molecule is the molecule with predicted highly predicted biological activity, that is IC50, and the higher docking score, that is D685001. Okay, for this we underwent for the 500 nanosecond simulation study. We have set up certain parameters like we have used Desmond software 2018 version. Only one option, post-field option, is available in the Desmond OPLS, having two versions, 2005 and 2004. Then we have used SPC solvent model with the grid box size of 3 by 3 by 3. Then we have added 0.15 molar sodium chloride buffer in that. 18 sodium ion and 15 chloride ions were added. Then we have chosen NPT Ensemble, which is exclusively used to maintain the temperature and pressure during the simulation time period, for especially for the biological system. Okay, Then duration was 500 nanosecond. Then we have used a time step of 2 femtosecond, and we have achieved equilibrium with the Newswer thermostat and Martin Tobias clean barostat. Okay, these are the parameters which we have used during the analysis. See, the motive behind going for this 500 nanosecond simulation is to avoid the triplicate simulation. Okay, see, reviewer always, if you are going for the good journal, and if you simply have performed 100 nanosecond simulation, then they ask you to go for some other study like PCA or free energy landscape studies. Okay, to skip that and to skip the reviewer question on the comment on the triplicate MD simulation, you can simply run 500 nanosecond simulation or 300 or 400 nanosecond simulation once, to avoid this type of cross question during the review process of the submitted article. Then key metrics which are evaluated are RMSD, which we have discussed earlier, RMSF, then radius of gyration, hydrogen bond analysis, and free energy landscape, okay, which we have performed with the script, which is in-house developed script. Then the results are we have obtained the RMSD value of 1.5 for the compound C8781660, which is very stable, plateaued early and maintained equilibrium throughout the simulation. Then for another ligand, that is D6850061, we have achieved RMSD of 2.7 angstrom, which indicate moderate stability, higher fluctuation, with a higher fluctuation that suggests flexible binding conformation. Okay, these are the graphs which I have obtained and available in the published manuscript for the RMSD. So this is RMSA plot. Okay. Is there any question on this? Then this is the interaction of the hydrogen bonding interaction or protein interaction contact of ligand during the 500 nanosecond simulation study. Then this is the comparative timeline plot of key molecular dynamic parameter for both ligand C8781660 and D6850061 with the PDB in complex with the PDB 1W11. Then this is torsion angle distribution and conformational analysis of ligand for ligand C878 and 1660. So thank you very much for your patience and once again giving me the opportunity to conduct a session on molecular dynamic simulation. Okay, if you have any query on simulation topic, then you can post in chat box or you can directly ask the queries.
In chat box, many questions are there. Can you please refer?
Okay. Yeah. See, is there any specific standard value for the RMSD and RMS? See, for RMS, there is no specific value. Okay. In RMS, we simply observe the fluctuation of the protein when it is bound with the ligand molecule during the entire simulation time period. Okay. See, if we analyze before also I explained that if we analyze the protein, single protein without any ligand or nascent native protein for the MD simulation, and further if you analyze for that, we observed higher fluctuation in the RMS. And when we then analyze the the drug ligand complex under the same condition, we observed the less fluctuation. Okay, but in RMSD there is a specific standard value of 3 angstrom. Okay, which is reported in the literature, and if your RMSD going beyond that 3 angstrom, it means that the ligand can't able to sustain contact, or the ligand can't able to maintain stability throughout the simulation. Okay. So, sir, what should be the value of RMSF and radius of gyration for good stability? See, RMS के लिए कोई value नहीं है. There is no specific value for the RMSF. We simply observe the fluctuation, and if the fluctuations are less in the ligand bound state, then the drug ligand complex is stable. But radius of gyration having certain standard value, it should be it varies from protein to protein. In certain cases, it is 22 or below 20. But the RMSD value of the drug ligand complex should be less than the RMSD value of the native protein or the protein with no ligand. Right. Then, sir, how we can say that ligand and the protein are stable? What are the criteria for it? Like in docking, on the basis of binding affinity, we consider it as a better. So for simulation, is there any specific criteria? See, during the key parameter analysis, we analyze the stability of the drug receptor complex for the RMSD value, RMSF value, hydrogen bonding contact, then radius of gyration. Okay, on the basis of this, we can establish that the ligand molecule is stable in the protein ligand complex. See, somebody asked me MMGPS. Okay, so MMGPSA is a technique which is performed after after molecular docking as well as molecular dynamic simulation. Using this technique, we can find out the binding free energy. Okay, of the drug ligand complex, a drug receptor complex. Is there any query on this topic?
Sir, one more question is there.
Yeah.
I think in initials you have mentioned that we have to remove some bad contacts while run the MD simulation. So
Yeah,
how
that
to
I
find
will
out how to find out the contact is good or bad?
see. A bad contact correspond to such atom uh, which is uh, which is not bound to the protein, or which is single atom like, or some water molecule which is not a part of that um, protein molecule, or which is not a part of system. In that case, we have to remove that. Okay.
It will identify by us or software will tell us.
It will identify it in the software itself. Okay.
Okay.
So while demonstration, I shall show you how to remove such type of bad content.
One more question is there. How we can say that our ligand and protein are stable? What are the criteria for it? Like in docking, on the basis of binding affinity, we consider it as better. So for simulation, is there any specific criteria for value?
See, for radius of gyration, for we evaluate the stability of the drug receptor complex using MD simulation. Under that, we evaluate various parameters like RMSD, RMSF, then radius of gyration, hydrogen bonding. On the basis of this, we can come up with the conclusion that the drug is stable in the receptor complex. And for RMSD, if it fluctuates, if the uh, end of the simulation, if the simulation ended with the, you can see here, is it visible to everyone? RMSD plot.
Yes.
See, यहाँ का जो RMSD है protein का, I'm talking about the blue lines. Okay, this red correspond to the ligand and blue stand for the protein. Okay, so you can see on the left hand side, the protein RMSD is 2.7, 2.5 maximum. Okay, so this protein is fluctuating below 3 angstrom, but still in this paper, the reviewer raised one question like the protein is stable, but the ligand is highly fluctual. Okay, so he suggests me to redock the ligand into the same protein with the same condition, and again upload that result in the supplementary material, so that we can say that after repeat simulation, the ligand showing same behavior with the protein or showing same RMSD value. Okay, any other question?
Okay,
So thank you.
last
Yeah,
question
yes, yes.
is there. Can we perform MMGBSA, PBSA in GROMAC?
Yes, sir. GrowMax, we can go for MNGBSA, but we need valid license, commercial license to perform that. Okay. So this placement is freeware and it is commercially free. You can install the software in Ubuntu in Linux system, and it is easy to operate. It is Ubuntu is you can operate Ubuntu software by using simple click technique. You don't have to write one command for that for running the simulation.
Thank you very much, sir, for answering all the queries and confusions.
Thank you,
Now,
sir. Again,
do you want any break or we continue with?
yeah, sir. We will have one 10-minute break. Okay,
Okay,
and we will
okay.
resume the session with the molecular docking followed by the MD simulation. Okay.
Sir, I think start with MD simulation because theory just we have
Yeah,
clear.
yeah, yeah. We will.
So in afternoon sessions, we'll start with docking.
Okay, no issues.
Okay.
Thank you.
Thank you very much, sir, for insightful sessions. So participants, we will have a 10-minute break. You may leave and be joined within 10 minutes. Thank you. Yes, sir.
So in this session, training session, we are going for the demonstration of MD simulation with Maestro. But before beginning the MD simulation, we create one folder, new folder, MD simulation. Okay, this is what we have created a folder. Okay, so we basically we analyze the stability of the drug receptor complex. Okay, via MD simulation. For that, we need one complex. Okay, I have some previously studied docking complex like uh, this is docking complex. Or we can download any PDB from the protein data bank. Okay, this is we have the complex of hit molecule number 4, and now we are posting that complex the created folder MD simulation training. Okay, now we have the docking complex for performing for studying for MD simulation. Okay, then I'm opening the software called Desmond. Okay, you can see This Desmond is installed with some other modules, that is material science, Maestro, Element, and Bioemulet, but this will not work. Okay, so in Desmond, Maestro only work, and it appears like Scodinger only. Okay, here I have opened the Desmond software. Okay, so the first step while beginning the MD simulation is the change working directory. Okay, so I'm going to the desktop and I'm selecting the same folder where I have saved the docking complex. Okay, here I have saved the I have selected the folder. Okay, then second I will import the drug ligand complex into the workspace of the Desmond. Okay, here directly going to the same folder which is selected in the chain working directory. Okay, so I am opening this the complex of hit number 4 with the SARS-CoV proteins. Okay, you can see the complex of the protein and the ligand. Then second step is to prepare the protein ligand complex by protein preparation wizard. Okay, so for this you have to click on the right upper corner. You will observe the horizontal line, 3 horizontal lines. You have to click on that, and in search you simply have to put type protein preparation wizard, or here it is available. That's why I'm directly selecting. Okay, after selecting this type of dialog will appear. Then in this dialog you have to go to the interactive. Then from this interactive panel we can directly get the PDB. Okay, it will connect to the, if I put any PDB code like 6LU7 like, then I can directly this Desmond directly download the PDB which we further use for the analysis. But here we don't require that. You can see the Desmond directly downloaded this PDB. Okay, but we will use the PDB of our ligand, okay, which we have taken in the created folder. So I'm selecting this one, and I'm going for the protein preparation of this. So after specify protein, we have a pre-process menu or pre-process panel. In that, we simply have to click the pre-process. Okay. So the pre-process will finish within a second of time. Then we check the structure further. Okay. So here we don't have any bad contact, or don't have any water molecule which is present separated in the workspace. Okay, so in this case we don't have to delete anything. Okay, we simply have to go to the protein workflow, and we have to go for the fourth step, that is optimize. Okay, now optimization will give rise to the formation of the flip of the protein module. See, we cannot achieve a similar protein preparation like a protein preparation wizard present in the Scodinger software, but this will create the comparable protein structure, which we can use for the further use for the system building, and further for MDA simulation. Okay. So here we have end protein preparation wizard. Then second step we have in MD simulation is the system building. Okay, so this is system building wizard, which is called as system builder, and this is used to form the boundary around the protein and addition of the various ions. Okay, this system builder is divided into two parts: solvation and the ions. Okay, so first we have to work in the solvation. We have to add salt. Okay, like while discussion I told you about the addition of the salt, like some particular number of sodiums were added, particular number of chloride were added. that together form a sodium chloride buffer. Okay, then I click on the recalculate. Okay, so that it calculate how many how many numbers of uh, uh, ions were added, salt positive ions were added during the simulation. Okay, then I am going to the solvation module. So here we can select the TIP3, which is predefined, and here grid box size is mentioned, different sizes are mentioned. Okay, so I always go for orthorhombic, or we can go for the cubic also, but orthorhombic is recommended in a lot of literature. That's why I'm going for this. Then I'm clicking the show boundary box. Okay, and after clicking the show boundary box, I'm adjusting the distance. Okay, I'm reducing this distance from 10 angstrom to 6 angstrom. Okay, so if you reduce this distance, then the protein side gets the number of atom size get reduced. Okay, तो जितना बड़ा आपका बॉक्स रहेगा उतना सिमुलेशन का टाइम वो ज्यादा लेगा. That's why I'm reducing the distance from 10 to 15. And after reducing the distance, first we have to predefine, that is TIP3. Then I'm clicking the show boundary box. Then I have reduced the distance, and finally I'm clicking minimize volume, so that the protein molecule get entered into the boundary box. Okay, and finally I am hitting the run button in system builder. Okay, so you can check the status of your job in the view analytic job option in the right upper corner. You can see here. Okay, so we can check and monitor the status. Okay, it will take 1 or 2 minutes to finish. Okay, okay, here it is finished, and now you can see while discussion I discuss about the boundaries of different physiological line. Okay, here you can see the boundary. Okay, now with the system we can go for the MD simulation. Okay, we will go for the final run of the MD simulation. So on the right upper corner you will find 3 horizontal line. You click, you have to click that, and you have to select the molecular dynamic simulation, and finally the panel of molecular dynamic simulation appear. So the first step in the molecular dynamic panel is the load molecule from the workspace. Okay, if you have molecule which is whose system is built in another computer, then you have to go for the import from file. But here we already have molecule in the space, therefore I am hitting the button load molecule. Okay, so that you will it will report how many atoms are there in the system, entire system. I think there are 24,173 atoms in the system. Then another step is simulation time. Okay, so this is just for training purpose. Therefore, I am just putting 2 nanosecond simulation. Okay, so rest of the things are default in the molecular dynamic simulation dialog box, and here you can give the name of the brain MD brain underscore MD as a job name. Okay, then you have to hit the run. Okay, it will take some 5 to 10 minutes to finish the 2 nanosecond simulation. Okay, then here you can check the status again. First it performed 7 different steps, and from 8th step it actually begin the molecular dynamic simulation. Okay. We have till that we can discuss queries also.
Participants, if you have any query till now, you can post in chat box or directly you can ask to sir.
Good morning, sir.
Okay.
Sir, I want to ask one thing. In Windows, in Schrodinger, can we perform MD simulation, or it's compulsory to use?
Ubuntu.
Yeah.
See, in Windows also we can perform the MD simulation, but
Okay.
Windows setup is not matches, or we can say Windows do not use GPU, that is graphic processing unit, to perform
Sir, I
the
have
high-end
sorry,
calculations.
sorry for interrupt, sir. I have Ultra 9 GPU system. So in that
Okay,
I
then, but still it do not use that GPU. Okay, we previously tried with the window. The window on which I am running having i9 processor with a 32 cores. Okay, and 14
yeah.
generation. But still,
Okay.
it take a lot of time. Okay, you can run on the window, but it requires a lot of time.
Okay, sir. Means we can run, but
Yeah,
it takes times.
it take time. But
Okay.
in Ubuntu, you can able to finish this within a short duration of time.
Okay, sir. Only timing issues there, rather than we can perform
Yeah,
according
yeah.
to you.
Rather we can have, but we have to incorporate special setup to use GPU during the MD simulation run. Okay, especially in the window. Okay,
Okay.
क्योंकि when we try GPU based molecular docking, it will take a lot of time.
Okay, sir. Sir,
Okay,
spatial setup
if
means I don't
we
understand.
have to, I don't have much idea about that. My colleague is there, Dr. Devanjan
Okay.
Sen. He developed certain module so that the window utilize the GPU to run the MD simulation. But I recommend you to run the simulation in Ubuntu only. Okay. Once you
Okay,
have
sir.
installed, then it is very easy to use this Ubuntu MD simulation in Ubuntu setup.
Okay, sir.
Yes.
Thank you
There
so much,
any?
sir.
Sir,
Yeah.
hello, sir. Good morning, sir.
Yes.
Sir, what about Google Colab Pro? Actually, OpenMM. What do you think about that, sir? We use the OpenMM
With the
interface.
help of using both OpenMM and Google Colab, we can
Pro,
run
yeah,
the MD
Colab Pro.
simulation.
Actually, yeah. Actually, we can
Yeah,
buy the a Tesla one GPU,
yeah,
A100. Yeah.
yeah.
So,
So that is
hmm.
okay. You can run on that, but Google Colab का एक problem है कि वो कुछ देर बाद बंद कर देता है, and it asks for the fund
No,
to
sir.
continue your simulation.
There are some Java code which make your laptop and your run to keep caffeinated. So my
Yeah,
question is,
yeah.
sir,
I haven't experience of that, but I
yeah,
simply read somewhere like.
sir, what about reliability, sir? Is Gromax is good, or sir is OpenMM? Since Gromax is pure CPU based MD simulation.
Yeah, I haven't used that, but both are comparable. So
Okay.
I published more than 100 manuscript with MD simulation,
Okay.
the same test one, but nobody raised any concern about that. Okay.
Okay, fine. Thanks.
Yeah, so you can go for Chromax if you have license, commercial license to use.
Yeah. Okay, sir, thank you.
So you can check the status of your job. Okay. See, in Ubuntu, I can't able to see the chat box. Okay, you can directly ask the query. Apart from when we compare this Chromax and the Desmond, I think Desmond is more handy as compared to Chromax, because there is expert person is required to install GROMACS, and even if you don't have any knowledge of script, Python language, you can simply run this Desmond. Okay, so you need some expertise to install that. So I think I prefer to have this one, Desmond. Okay, we are running 2 nanosecond simulation for the in-house drug receptor complex print from the docking study. Sir, do you have any query on this demonstration?
No, sir.
Okay, so it's very easy to run that simulation, except some interpretation part is there. Okay, let me minimize this, and I shall show you the how we interpret the docking data. Okay, here is the data file we obtained in the simulation result. Okay, you can see the same docking complex. Is it visible to everyone?
Yes, sir.
Yeah. So this is simulation interaction diagram report. Okay, you will find all the diagrams. Okay, it generate one combined report. Okay, here your job name is there. Desmond MD job MDR1. Then entry title is there. Hit number 4 from 200 hit complex with PDB. Then this is protein information. Then this is ligand information. Okay, you can see the structure of the ligand along with the structure. Smileys of the ligand along with the structure. So number of atoms, atomic mass, charge, everything it mentioned in the report. Then counter ion. Okay, you can see how many counter ion, that is chloride and sodium and the chloride used during the simulation. So 22 sodium ions were used with the concentration of 61 millimole, and chloride 18 chloride ion were used with the concentration of 15 millimole. And the charges for these ions are 22 for the plus 22 for the sodium and minus 18 for the. Okay, this is RMSD plot obtained after 150 nanosecond simulation run. Okay, here we have finished the simulation. Okay, let us analyze the after finishing once the simulation is finished, we have to close this one. Okay, we directly have to go this one. Then on the right side panel, we got 6 number file, the new file which is generated after completion of the MD simulation, that we have to click first. Okay, so this is what the files we obtained after at the end of the simulation. Then to analyze the result of MD simulation, we have to go for simulation interaction diagram. Okay, so we have to click on simulation interaction diagram. So here we have the simulation interaction diagram panel. In this panel, we have to go for load. I'm clicking on load, and I'm going for the Desmond MG job train MD. Okay, so we will have 3 different files. Okay, Desmond MD job train MD trajectory, then Y, and out.cms. Okay, from these 3 files, we have to select the md-out.cms file. Okay, to analyze the simulation result. Okay, here I am opening this, and again one more panel, one SID analysis setup. So in this panel, we have to select all the options because you have to analyze all the parameters. If you are selectively going for the analysis, selectively going for only RMSD analysis, then simply you have to select the RMSD. Then only protein ligand detail along with the RMSD plot will appear. Rest of the parameter will not be assessed in the simulation result. Okay, So as we are going for all the parameter analysis, therefore I'm selecting select all. Okay, and finally I am hitting the run button in this SID panel. Again, I have to click start. Okay, now the analysis is started. Okay, within a couple of minutes, the analysis gets finished, and we will observe the simulation results. So this simulation interaction diagram sometimes take 10 to 15 minutes. It depends on the number of atoms present in the system, because it is analyzing 6 to 7 different parameters from the MD trajectory, that is out dot CMS file. Okay, once this analysis is finished, one more screen appears, and that screen contains all the parameters which we have selected in the simulation interaction diagram analysis. So you can see the screen appears. Okay, this is RMSD plot, and you can see the protein. This blue fluctuating line stand for the C alpha chain of the protein molecule, and the red fluctuating line stand for the ligand molecule. On left side, we can measure the RMSD of the protein. On our right side, we can measure the RMSD of the ligand molecule. Okay, here the ligand molecule have achieved the RMSD of 1.30. This indicates that the protein ligand complex is shared. Then after this, we have fluctuation. Okay, here we can see this is RMSF plot. Okay, on the x-axis we have a residue. Okay, residue numbers, and on y-axis we have a RMSF value. That is root mean square fluctuation. Okay, so here these green lines are appeared on the some ridges and furrows in RMSF plot. If you put cursor on that, you will find which chain is there. Whether chain A, B, C is there. What is the RMSF, and what is the name of that particular residue? Okay. So likewise, we can this will be helpful during the analysis. Okay. This is a threonine residue, and again we have one more residue here, and this residue bound with the ligand and reduce the fluctuation of the protein during the simulation run. Okay, then after that we have a ligand RMSF. Okay, the ligand RMSF will appear like this. In MD simulation, ligand RMSF don't have that much importance, because we emphasized on the protein stability in the MD simulation. Then another important aspect is protein ligand contact. Okay, so this interaction, this is bar plot we referred, and this indicate the different type of interaction executed by ligand molecule during the 2 nanosecond time scale. Okay, so the green stand for the hydrogen bond, pink stand for the ionic interaction. Here no peak is available. Then hydrophobic, this magenta color stand for the hydrophobic contact, and blue color stand for the water bridges. So throughout the MD simulation, we observed some 1, 2, 3, 4, 5, 6, and 7 hydrogen bonds. Then there is no ionic contact. Then we have some hydrophobic contact like one with the residue like MET49, then MET165 and PRO168 residue, and rest of the water bridges contact. Okay. See the another diagram which is present below this bar plot is the contact histogram. Okay. Here you can see on the left side you will find the vertically arranged residue along with their numbers, and from that you can find which residue gave rise, which residue executed more and more contact. Wherever you find a dense region, okay, so that residue like threonine 25, then this proline 168, 189, these form significant contact during the molecular dynamic simulation. Then this is 2D interaction diagram for the ligand with the receptor. Okay, you will find a lot of water molecule, and you can correlate this interaction with the bar plot. Okay, then there are some this blue line indicate a hydrogen bond. Okay, so this is simulation. This is 2D contact. Then ligand torsion is there. Okay, and these are ligand properties. Okay, so here no intramolecular hydrogen bonding contact is detected. Okay, if you find any intramolecular contact, that is interaction within the ligand molecule, that simulation is not a good. Okay, so this property like RMSD, radius of gyration, molecular surface area, solvent accessible surface area, and polar surface area stand for the ligand molecule, not for the protein. Okay, so this is all for the this all analysis related to the MD simulation results. Okay, do you have any query? You can directly ask the query because I can't able to see the chat box. Umang sir, is there any query on demonstration of MD simulation?
No, sir, no any query, but one question is there. Is
Okay.
Desmond is free software or we need to take license?
Yes, Desmond is free software. You can use anywhere for your work. Okay. I shall share with you the link to download the Desmond. Okay. So all of you can download and enjoy your work with Desmond.
Anybody else having any query? Participant? You can post your query in chat box. We have still 5 more minutes. If you having any query, you can post it.
Okay, I'm stopping the sharing of the slide so that I can see the queries of participant. Yeah, I have seen one query: is Desmond free? Is 25 nanosecond run enough? So it depends on your work. Okay, if you have good number of protein ligand complex, then it takes a lot of time. If you have some 10-15 complex, then and in that case, if you are achieving stability in 20.5 nanosecond, then you can have that. You can go for 20 nanosecond. Okay. So for one of my colleague, that is one of my friend, Sapan Shah, he analyzed his 20 drug receptor complex for MD, and in that case, we have ran only 20 nanosecond simulation. Okay, it was his PhD work, so it is okay. There is no such recommended time period. But in case if you are not getting the stability of the drug ligand complex at 20 nanosecond, in that case, you have to extend your simulation time. Is there any query? Okay, thank you so much, Umang sir, for your patience, and thank you so much, participant, for giving me the opportunity to present a demonstration of MD simulation run and its analysis. Okay, thank you. Yeah, I'm sharing the link now. Okay.